My name is Mario Porrmann, and I will now continue and give you some first insights about what we did with respect to performance evaluation, especially focusing on the reconfigurable accelerators that we are developing or starting to develop within VEDLIoT. So again, the big picture, and Kevin already gave an overview about the big amount of hardware platforms that we are using or that we can use here in VEDLIoT. And this talk now is about the FPGAs and how we want to utilize the FPGAs. So how do we develop what is the current status of FPGA-based accelerators in VEDLIoT? We want to enhance the efficiency wherever possible, utilizing, for example, dynamic reconfiguration. How do we think about this? And I will give you first results on performance of the FPGA-based accelerators, as already pointed out in the slides from Kevin. And finally, we will see if the first implementations will be based on Xilinx UltraScale with integrated ARM processors. We are also working towards a more open platform, let's say, and I will comment on this, on the workflow for configurable soft SoCs. So you've seen this picture sometimes now, and there are unfortunately some numbers missing here. So it's the different types of the REX architectures and of the REX platforms. And what should be visible here is hidden behind the green boxes maybe, is the amount of FPGA resources that are available. So in the micro REX you have about 100 K logic cells available on FPGAs. In the T-REX, it's in the order of millions of logic cells, and in the REX boxes, it's in the order of 10 million logic cells, which are available inside the platforms. For the micro REX, on a single FPGA module, and for the larger REX systems, then on multiple FPGAs. So what we need is, first, to start, we need an FPGA-based architecture which integrates all the required interfaces to the outside world as well as to the accelerators. We wanted to have support for dynamic runtime reconfiguration to enable exchange of accelerators at runtime. And later on, we need also deployment mechanisms, and we here especially want to focus on the migration of tasks from one FPGA to another. So reconfigurable modules on the FPGA moved between the FPGAs. So about the basic FPGA infrastructure, so there we started based on the micro REX. And the idea here was to have a simple block-based design which enables an easy customization of the FPGA platform utilized in the micro REX. The front end is based on the standard Xilinx Vitis tool flow, and we are able to add additional optional IP cores, of course, and here we want to utilize especially LightX. This is interesting, especially then later on if we go to the soft SoC platform. For the implementation, we use a complete scripting-based approach so that the user typically doesn't have to deal with the Vitis environment. He just calls some scripts. There are configuration files which define the board architecture and the accelerator, for example, so that you can easily port your base design with your accelerator from one FPGA to another FPGA or to another FPGA platform. Here, of course, for us important is moving from micro REX to T-REX to the REX box and the different FPGAs and FPGA boards. Well, the hardware integrates all the required interfaces for the communication, like, for example, Ethernet, PCI Express, what is required here in this example for the micro REX. And of course, especially for micro REX and T-REX, for the sensors and actuators, which can be directly connected to the hardware platform. Important is to enable easy access for software developers, therefore the scripting-based approach, so that you don't need, in the best case, too much FPGA design know-how. And for utilizing this, it's based on PIDA Linux, which enables easy access to the complete system and especially to the accelerators then for the software developments, for the software developers. Well, and this is all integrated in the microrex, but as Kevin has shown, the microrex is still under development. So what we did is we built a small test bed, like an emulation system for the microrex, which is based on available off-the-shelf components and development boards. So this is how the architecture then looks like. Nothing surprising here. We have the processing system. In the ultra-scale architecture, most of the interfaces are directly provided by the processing system. We have the accelerator. In the easiest case, simply one big accelerator on the FPGA, and then there are additional I/O units, additional interfaces, which can be implemented in the programmable logic in the FPGA fabric. What we then did is, well, we want to build our own accelerators, but which is the baseline? So what do we compare to? On the one hand, we compare to the GPUs, of course, but we also wanted to have a feeling about what can be delivered on the FPGA, by the FPGA. So we did some first reference designs based on the Xilinx DPU, which serve for us as a baseline for the evaluation of the accelerators which are developed within VEDLIoT. For example, with the co-design approach presented by Pedro. Yeah, therefore, we integrated the Xilinx Deep Learning Processing Unit, the Xilinx DPU. That's a programmable engine for CNNs, for convolutional neural networks. You can quite easily integrate it into your architecture as an IP core, which is provided by Xilinx, and yeah, we use it on the Xilinx UltraScale Plus MPSoCs, which are currently mainly used in VEDLIoT. The interesting thing is that the hardware architecture of this IP core is configurable with respect to the parallelism, for example. So you can, in the table it's also shown, you can switch between a version which provides peak performance of 512 operations per clock cycle, and you can have larger versions with higher performance then. But you can also switch between memory or DSP usage, so going for architectures which mainly utilize DSPs or which avoid, let's say, as much as possible DSP utilization. We evaluated then our scripting-based approach and this on different platforms, from quite small FPGAs like the 3EG UltraScale Plus on the Ultra 96, that's quite well-known development board. We have the SMART module with the 4EG, still a quite small FPGA, and then larger FPGAs based on these larger modules, which then not fit into the microrex, but which can be used in the larger rex boxes. And then they go up to from 100K logic cells, order of 100K, to more than 1 million logic cells. This is an example implementation. I don't want to go into the detail about the table, but what we use there is this SMART module. It's a module from Seco called Russell, and well, one of the slowest 4EG FPGAs provides a quad-core ARM and, well, quite some FPGA resources. In this case, the base design requires about 10% of the resources. The rest is free for the accelerator. If you go for the larger FPGAs, then it's just like about 2%, which is required for the base design. As soon as you have this, you have to program the architecture, and there it depends on whether you want to go for like highest throughput or minimum latency. And the easiest thing, of course, you can do is to have a simple single-threaded implementation. You read the data, pre-process, do some processing on the DPU or on your accelerator, and then finally do some post-processing, store the data, whatever. This will be the minimum latency implementation on the one hand. But on the other hand, the problem here is that this will not be the implementation with the maximum, with maximum throughput then. Then you have to go for a multi-threaded implementation, and to ease the design, we built an environment supporting, we would call it semi-automated realization and evaluation of this multi-threading. So you put your application in a specific structure that we have defined, and then you can decide whether this should be like 2 or 3 threads and so on. And this enables for us to analyze like really the trade-off between latency and throughput. And then we measure the power. That's interesting, not only just to see how well we do it really right, we know exactly the power, but that's also interesting from a profiling point of view, because now you can really see when is there something happening. And now on FPGAs, that's quite nice. You can have like real timestamps showing, well, now I'm starting this operation, now I'm starting this operation, and this can be indicated here also clearly. So, for example, that the nicest pictures you get if you do this simply without multi-threading, then you can exactly see when the GPU processing starts and so on. And based on these measurements, then we go further and, well, did quite some design space exploration, first simply based on this standard GPU. And what we found interesting is that there is already quite a design space if we just decide which size of GPU to put there, how to utilize the GPU, and so on. And here are some examples with like quite small CNNs, like MobileNet, going to larger implementations like YOLO v4. The obvious things are shown here also. There's no need to utilize like big architectures on the FPGA if you have only small networks. And we see that like multi-threading helps. We see this on different FPGAs in different versions. Here on the small FPGA, like 2 threads is already sufficient, but delivers a significant speed up, or significant efficiency increase, let's say, in terms of giga operations per watt. This is displayed here in a bit different way. So here we have YOLO v4 and MobileNet, and just on the x-axis the power against the performance, like what we've seen also previously in like the other accelerators. And what we find interesting, not only here, but an important thing, is that there is quite a big space from low power implementations to like high performance implementations, to just mention the positive aspects here. This can be analyzed in this way, or on the other hand, for example, here comparing a like normal YOLO v4 version against the pruned YOLO v4 implementation. Here we have like the achieved performance in terms of inferences per second against the energy efficiency in Joule. And there also we see like what is the best implementation for a required efficiency, for a required application, let's say. So if we put this into the context of the diagram that has been shown by Kevin, well, we had there already these 2 implementations, like the 15 and the Z03, but that's not the only one. There is quite big design space around this, and we can now select like between low power implementations and high performance implementations. And what we think is interesting is, well, do we have to decide this at design time, or do we have to, or can we decide this later? So dynamic reconfiguration, even with these like simple, straightforward implementations, is an interesting approach. So the idea is that we can change the characteristics of the accelerator at runtime. of course, also can change the complete accelerator. So in this example, for example, we can change the performance power trade-off or the performance accuracy trade-off. And yeah, so we just need to make little changes to the design, and then this is simply based on the Xilinx tool flow for dynamic function exchange, so partially reconfiguring the FPGA. So we define a PR region, and now we can load accelerator A into it. The system is running. Then while the rest of the system is continuing, we reconfigure to accelerator B, and then maybe back to the first accelerator. Can be done in this way, can be significantly more flexible if we have like 2 regions with different accelerators, so that one accelerator can continue to continue execution while the other one is reconfigured, and the regions can even be subdivided to furthermore increase the flexibility. So for us, this is like now the baseline within VEDLIoT for our own implementations, and we will go for reconfigurable deep learning accelerators in these 2 areas, as mentioned before, like reconfigurable in the sense of configurable one time and dynamically reconfigurable. So as a like tool for the co-design approach, which Pedro showed, we need to be able to have lots of different possibilities to generate accelerators. And here we go towards an approach comparable to Finn as presented by Pedro in his talk. And the idea is to generate a data flow architecture based on C++ templates. What is maybe a bit special here is that we want to support inference and training, so that we can, on the one hand, of course, target CNNs, but we can also target deep reinforcement learning and federated learning, for example. So we define parameterizable layer templates in C++ for the layers which are typically required, and they are parameterizable, for example, with respect to quantization. So, for example, providing like very low bit widths up to like, so going down to 2, 3, 4 bits. And then we can also select, if we want 3 bits, we can just go with 3 bits. But we can also go to float, and that's another important thing, because we also want to support learning there. The layer implementations will be optimized for high-level synthesis, and the layers then integrate the required functions, like the forward and backward propagation and update functions. Inference will only utilize the forward path, but for example, deep learning then will also utilize the full functionality. So far, everything was like very much focused on the currently available MP-SoCs from the vendors, especially Xilinx here now, and the processing platform there is then the integrated ARM cores. But we also want to go for a more open platform, and therefore I was very happy about the talks in the session before, because here also within VEDLIoT, we like in parallel to utilizing the MP-SoCs, we want to analyze soft SoC platforms. And they will be based on RISC-V, because the idea here is to have a very open architecture. And again, I mentioned this LiteX integration, which we are already now utilizing. So the SoCs will be generated utilizing the open source LiteX SoC generator. And the interesting thing here, not only it's all open source and so on, thinking about dynamic reconfiguration, we can now not only reconfigure the accelerator at runtime, but if we want, we can even reconfigure the or one of the processor cores at runtime if we want, switching between different implementations. So especially project partner Micro is working a lot on the tool flow for the configurable SoC. And here the idea is really to provide a workflow for the generation of SoCs with integrated AI accelerators, so that you can do design space exploration in a quite easy way, combining RISC-V processors with application-specific accelerators. So the idea is that the generator enables you to generate the complete system-on-chip environment with all the peripherals required, and you can go from simple microcontroller unit size implementations, RISC-V, up to Linux-capable platforms. The idea here is to have a vendor-independent accelerator integration, so that you can port your implementations of accelerators, for example, across lots of different hardware platforms, and everything should be done using open source tools. An important aspect here are the newly defined custom function units in the RISC-V standard, and they open up the possibility to add custom accelerators, which are tightly coupled to the RISC-V CPU and can then be accessed via custom RISC-V instructions. And Micro is also working there closely with the RISC-V organization in defining all these things. And then you can implement your accelerators totally independent of the description of the RISC-V processor, for example, like in new, quite abstract hardware description languages. So these custom function units offer great flexibility, and important is, if you want to do this design space exploration, you have to be able to test lots of different accelerators for the workflow. So you will not know from advance which will be the best integration, which will be the best custom function units, and so on. So you require good simulation frameworks, for example. And there, project partner Unmicro is proposing its Renode framework. So we have Renode and Canning as two important open source tools in this area. And Renode can be used as the simulation framework already presented by Pedro in the beginning. And this is, or has been extended with support for custom function units. So you can do the co-simulation of, for example, the functional model of your CPU, of the complete SoC, with cycle accurate, for example, in very later simulated custom function units. So based on this, you can do continuous integration testing with different CPU implementations, different input data coming in. So, and the tool also allows for automatic result comparison and analysis of the results then finally. Well, important, everything is open source, and that's the way we want to go, like starting from more vendor-specific things towards as much open source as possible. So you have already seen this slide sometime. This seems to be the end now. Will be the last time to see this today, probably. So this was the VEDLIoT presentation. You have learned something about the platforms, so the hardware, which is scalable, which is heterogeneous, and which enables us to add distributed accelerators based on GPUs, based on specific machine learning ASICs, for example, or based on FPGAs which allow us to analyze new architectural concepts. And, well, we have not talked so much about the tool chain, but yeah, there is significant work also towards optimizing the deep learning for the IoT use cases, which we cover: industrial IoT, automotive, and smart home. And very important, could also be your use case. So open call is still open for submission until 8th of May. So nearly 2 weeks to go. This will provide you the utilization of the software tool flow as well as the hardware. So if you want to get hands-on this cool hardware stuff presented by Kevin, this would be an easy way to go. Well, as easy as such a proposal is. Okay, so I will keep this one for the last, as the last slide, so that you know where to apply for the open calls. And yeah, I and the others too are open for questions. Thank you.